So thank you very much for the invitation and the opportunity to give a talk. So this is my first time in Korea. So it's a very warm welcome, also weather-wise, I noticed. Okay, so my plan is to first give you a little bit of, some reason why people looked at the topic of the remainder of my talk, and also some background information. Some stages will be maybe, I have to introduce a bit of technical notation, but I also try to point out the main line that you can sort of follow what is going on. So, K-theory and arithmetic. So let's start with the arithmetic as a motivation. So what I've written down here is the definition of the Riemann zeta function, the sum over all positive integers n raised to the power minus s, for s a complex number of real part at least bigger than 1. And by the unique factorization in the integers, you can also write it in the product shape. So in that case, you take a product over all prime numbers of 1 over 1 minus p, the prime p to the power minus s. Okay, so this works out because you have unique factorization. And if you develop that one using a geometric series and multiply everything out, you see that quite formally you get the sum. So it is known that you can extend this to a meromorphic function on the complex numbers, and there is a single pole at s equals 1, and the residue is going to be 1. Okay, and then this has been studied very for centuries now, and then it turned out that if you look at the values of zeta at an integer, if the integer is positive and even, then there is actually a closed expression in terms of, zeta to n will be pi to the power 2n, then times the rational number, which is very well understood in terms of Bernoulli numbers. But if you go to the odd integers, at 1 there is a pole, so you have to skip that one, so you can look at 3, 5 and 7, etc. And then almost nothing is known. So, maybe nowadays it needs a qualification, so it's a more classical result from the 70s maybe, that zeta 3 is irrational. And then sort of nothing was known for a long, long time. And I think the best result that I now know is that if you look at the next 4, so zeta 5, zeta 7, zeta 11 and zeta 9 and zeta 11, then I think it is known that at least one of those has to be irrational. But it's not known which one. Probably all of them, but none of that is known. Anyway, so there is a very marked difference between what happens at the even integers and what happens at the odd integers. And so how do you generalize this? Well, if you look at a rational skew, this is an example, the simplest possible example of a number field. And in general, you can get number fields by taking an irreducible polynomial with coefficients in Q, and then adjoining a root alpha in the complex numbers to Q. So you then get Q of alpha, which will be, in that case, you basically take polynomials in alpha, but because of the polynomial relation you have of, say, degree d, you can eliminate alpha to the power d plus 1, etc. And therefore you only have to end up with this. So, for example, qi, minimum polynomial would be x squared plus 1, and therefore you only need something to form a rational number plus a rational number times I. And it behaves in some sense very different from q, and in some sense it behaves very similar. So in there you can define a subset which would be, maybe on the next slide. So let's first look at the zeta function. So in this case you can look at the, you can also write down a zeta function of the number field. And you can look at the ring of integers, which I should be having here, yes. So you look at all the elements in the field that are 0 of a Moloch polynomial with integer coefficients. So the leading coefficient should be 1. And a priori, if you look at this set of zeros, this is only some kind of bizarre set, but it actually turns out to be closed under addition and multiplication. It will be a subring of the field K. But this is called what's called the ring of integers. Plays a big role in number theory. And actually, if you start with your number field Q and you write down this definition, there is a basic lemma that tells you that in fact you have found again the integer Z. So that's why you call them the ring of integers in general. And they behave a little bit the same in the sense you can write down the Riemann, the zeta function, the analog of the Riemann zeta function for this number field. And you look in this case in this ring, and you look at all the non-zero ideals in there, and you can form the quotient O modulo I. This will be a finite field, in the finite ring in this case, and you just look at the size of this and you raise it to the power minus s. Okay, so if you were to take your number field to be Q, then your ring of integers would be Z, and then all the non-zero ideals correspond to positive integers, and you would find that this will be exactly the Riemann zeta function. And just like the Riemann zeta function had a product definition, you can do that here as well. So in this case, you can look at the non-zero prime ideals, and you can also look at the corresponding size of the quotient. And then you can write down this product, and well, if you were to formally expand this and multiply it out, then you would get always sort of formally the norm, as this is called, of the size of O modulo product of prime numbers. And they actually coincide because any non-zero ideal in I can be written uniquely as a product of prime ideals. Okay, so even though in general such a ring of integers will not have a unique factorization like the integers at the level of the prime ideals, of the level of the ideals, the non-zero ideals in the ring of integers, that statement still holds. So let's see what people have been doing with this the zeta function. So first of all, you can extend it again as a meromorphic function on the complex numbers with a simple pole at s equals 1. The residue will be more complicated in general, so we need some notation for this. So, well, this number field came from a polynomial of degree d, and therefore we can look at all the possible roots in the complex numbers. So there will be R1 real roots, and there will be 2R2 conjugate pairs of, well, pairs of conjugate complex roots. Okay, so this will be a standard notation in so these are always R1 plus 2R2, and R1 corresponds to the number of real roots. And then you can, at this ring, you can look at the units, the group of multiplicative units, and this is then known to be, well, there's a free part of rank R1 plus R2 minus 1. And then there is some torsion part, which is going to be cyclic, and is going to be, well, the size is normally denoted W, it's the number of roots of unity in the field K. And then people considered all the embeddings into the complex numbers up to complex conjugation. So that means because, well, if I use a root over its complex conjugate, it will be the same up to complex conjugation. So I have R1 plus R2 number of such embeddings up to complex conjugation. And then what people wanted to make was basically a square matrix. I can take an embedding, sigma, and I can let it loose on a basis element of O star modulo the torsion, because the torsion will be a root of unity. If I take the absolute value, that would not be visible, it would only give me a factor 1. And then you can try to write down this matrix, pairing all the embeddings with all the elements of your basis. So the point is, it's not exactly square, because of this minus 1 here. Go for the old-fashioned way. So that means that you sort of have your one-off in one direction. So you solve this, at least in this incarnation of this definition, you solve this by putting a column with 1s in there to make it square. Then you take the determinant, and then you take the absolute value of the determinant, and then you put in some correction factors, because this is not the usual definition of this, what is called as a regulator R. Anyway, so this is some complicated number. And for example, if you were to take q squared of 2, then, well, there will be, in this case, R1 equals 2, R2 equals 0. This will be rank 1, this R equals 1. The units are generated by 1 plus square root of 2, and also the plus or minus 1, the 2 torsion. And this will be just ending up being a 2 by 2 matrix. And basically we'll be computing here the log of the absolute value of 1 plus square root of 2. So this was essentially the number that would come out. Anyway, so then this regulator is related to the residue at s equals 1. So this is also sort of classical formula now. You get 2 to the power R1, sort of 2 being the size of the one-dimensional circle, meaning 2 points. 2 pi to the power R2, that's the size of the complex circle, because now we have the complex embeddings. Then you get this regulator, and then there are some other numbers. So there is the size of the class group of O, that is some finite abelian group that measures if O has unique factorization or not. So there is unique factorization in O if and only if the class group is trivial. Then we get the size of the torsion in O star, the roots of unity, and then there is something, the absolute value of the discriminant that is also, well, I don't want to define it. It sort of shows up all the time in this kind of game. And so this is, I think, from the 1870s or thereabout, maybe even earlier. And well, then you have to sort of wait for a little century. And then in the 1970s, people were defining K-groups. And so once they did that, and I'll recall or sketch a little bit how you define the low ones, and then they realized actually that this very old formula contained all kinds of K-theory. Because it turned out that if you take the K0 of the ring of integers, this is a copy of Z, basically corresponds to something like a rank or a dimension of a vector space, and there is a small torsion part which is isomorphic to the class group of O. And K1 of O turns out to be, in this case, the unit of the ring O. And therefore, if I look at this W, this is actually just the torsion in K1 of O. That's the torsion in the units. Okay, so basically this regulator came from O star, which is K1. The class group corresponds to the torsion in K0, and also this W corresponds to the torsion in K1. So this very old formula contained lots of K-theory, as they discovered. So they thought there should be maybe more of a link between, for example, zeta functions and K-theory. So let me now sort of sketch a little bit what people were doing with K0. And so we're going to switch to a rather different topic at the moment. So let's just take a commutative ring with 1 for simplicity and not equal to 0. And then, well, K0 was set up to have a certain universal property if I have a short exact sequence of sort of coefficients in cohomology, by which I mean that I have maps like this, and every time I sort of go from A to B to C, then the composition is a 0 map, and moreover, if I look at the kernel of this map, it should be exactly the image of the previous one. Okay, so in this case, so this is exact. That simply means that this is a surjection, this is an injection, and the kernel of this map is exactly this P prime. And it's sort of, well, in topology, etc., algebraic topology is a principle that if you have a short exact sequence like this, then you usually get something like a long exact sequence, which is also going to have some kind of period modulo 3. And K0 was supposed to sort of then say that what you have in the middle is basically the same as what happens on the two things on the outside together. So this is sort of formalized as follows. You take sort of a nice module, finally generated. So module basically means vector space, but then over a ring. You assume it's going to be finally generated, and then there are two things you could demand is going to be projective, or you could ignore this. So projective actually means that if you have any surjection, you can split it. So if I have any surjection, then B will sitting inside this M as a direct summand. So that means here that if everything here is projective, then this P is actually going to be a direct sum of this guy plus the kernel. Okay, so P is the sum of this one and this one, and that's exactly the relation you're going to put on here. You're going to take a free abelian group on generators, finally generated projective R modules, and you then impose exactly the relation that the generator for P is the sum of the generator for P prime and P double prime for if you have this. So you could actually also delete the word projective here, in which case you can use a similar definition. You may get a different group, but in that case this splitting is no longer guaranteed, so it may look more interesting and maybe more natural then. Anyway, this was set up to have some universal property, and if you take your R to be a field, then finally generated, well, an R module becomes a vector space. Finally generated means finite dimensional, projective is guaranteed, everything is going to be very simple. And then you see that the only interesting thing you can actually look at here is the dimension. Okay, if I have two-dimensional space, I can take a one-dimensional subspace, take a one-dimensional quotient, and therefore you just split everything into a copy of the one-dimensional space that you naturally write down. So that means in the end that K0 is just going to be Z of this field, and this is some kind of generalization of the dimension. You can do something similar if you have an abelian group, so that will be a Z module. And then projective means free, and then you can do the same game. You basically just look at the rank of a free abelian group. And more difficult, if I take a number field and I look at the ring of integers in there, then it turns out that K0 is, well, Z, basically something like the rank. And then there's this little torsion part, which is this class group, or isomorphic to the class group. Okay, so people define K0, and therefore they try to construct some short exact sequences. In fact, in the beginning this was just called K, because they didn't realize that it wasn't quite what they wanted maybe. So they tried to build some exact sequences, and then there are only 3 terms. And in cohomology that means you need another functor to put on, you need another 3 terms with a different index. So they start to define K1. in order to get longer sequences. And I wasn't around at the time. Well, I was around at the time, but not in mathematics. And so somehow they thought that if K0 is built from modules, say vector spaces, then K1 should be built from the relations among the vector spaces or the modules. And that basically means matrices, the maps given by matrices. But the fun is the matrices are of arbitrary size, so we take GL n R. That simply means that matrices coefficients in R size n with determined unit in R, so they are invertible. And then you sort of make the size arbitrary by just sticking rows with zeros and a 1 in. So you can take the union and you don't worry about the size any longer. So that is denoted GL of R. And then, well, whatever they thought that K1 of R should be abelian. So there's no simpler way than making it abelian than by taking GLR and just quotient it out by the commutator subgroup. Okay, so guaranteed to be abelian. And, well, you can take a determinant. And the determinant of a commutator is going to be 1. So it will factorize. You give a surjection from K1 of R to R star. Okay, and there may be a bit more in the kernel that you then call special, that you call SK1. So you at least have given it a name. Now, if you teach linear algebra, then you basically teach them that K1 of F equals F star, because you can just compute your determinant with simple operations that are actually, it turns out, in this commutator. The same proof would be basically working for any principal ideal ring like Z. You can compute the determinant in a simple way, and you would find that it's only the units. So much harder is that the same thing holds if you have a ring of integers in the number field. It will not be principal ideal domain or anything nice like this, but it's still true, much harder to prove. And just before you get the idea that this SK1, this kernel, is never there, I've written down a simple example where you have a huge kernel. I don't want to go into it, but anyway, it's sort of easy to give examples in the sense where this SK1 really means something, or means something, at least it's there. Okay, so that was K1. And then they had the same problem as before, basically. They had a longer exact sequence, and now it's 6 terms as opposed to 3. But they still wanted to lengthen it, so they needed something that is going to be called K2. And again, I wasn't around at the time, but if K0 was built on the modules, K1 was built on the relations among the modules, meaning the maps, then K2 should be built on the relations among the relations among the modules. Okay, so relations among matrices. And well, this is what they came up with. So you look at elementary matrices. So you're going to take an element R in your ring. You're going to put it off the diagonal at the identity matrix. So you get something that is called EIJR. And then by simple calculations, you can see that there are some relations they should satisfy. Okay, this is essentially row and column operations. For example, doing the same operation with an R and an S will just add up. And you can also compute a commutator depending on the indices. So in general, they would commute if there is no link between the indices, but in certain cases you actually get another elementary row operation. So by the way, this tells you that if you have 3 by 3 matrices at least, every elementary matrix like this is actually a commutator. So working modulo commutators will mean certainly working modulo the elementary matrices. Okay, and you can actually show that the elementary matrices here, they're inside, you can actually show that they generate if you don't care about the size of your matrices. And well, then they define the following thing for K2. Okay, so they then took a free group, not free abelian, but a free group on generators X, I, J, R, which are going to be behaving exactly the same as the previous one. So we just take a free group and then we impose relations like we have here. So we just replace an E with an X everywhere, and then we get some relations that we impose on the X. So that will be the quotient that you get in that case is going to be called the Steinberg group. And by construction, you have a map from the Steinberg group to, well, the elementary matrices, which was exactly this commutator subgroup of GLR, by mapping XIJR to EIJR. Okay, the relations that we impose are satisfied on the right-hand side, so this thing exists. It will be even surjective. And then they defined K2 of R to be the kernel of this map. Now they had this desire for abelian k-groups, and it's not clear at all that this thing will lead to an abelian k2, but it actually is an abelian group, and in fact you can show that this k2 is exactly the kernel of, sorry, is exactly the center of the Steinberg group. So, well, this is certainly enough. Beyond this, life became quite difficult because they sort of couldn't go on with K3 in an elementary way, and it was only when Quillen came along who first defined K-groups for rings, as we defined here, but then also K3, etc., and also for schemes, or the varieties in, which we'll use a little bit later. Anyway, so let's see a little bit what we can say about K2. So for a field, you can actually make it more explicit, although it's still not very explicit, but we see right down generators. So you end up with symbols. Those are not sets, but they are symbols. And you can imagine this is also notation they chose before they were latexing everything in order to publish it, because it's not very useful to, not very nice to type. But you take pairs, ordered pairs A, B with A and B units in the field. And then you're going to impose relations, so it's essentially bi-multiplicative. A multiplication here in the first one will correspond to an addition here, and the same for the second. And then the most surprising thing is maybe that if the two things add up to 1, then this symbol is trivial. It's called the Steinberg relation. And then it's an easy exercise from those three to see that in that case it's essentially alternating. A, B equals minus B, A, and C, minus C is going to be trivial. Okay, so, and if you want to know how this is done, you can check that those matrices are actually in this commutator GL, and this thing here as well. And then you lift them in the Steinberg group, you take the commutator there, and then you, because those matrices commute, this commutator will be in K2 of F. It's well defined. So that's basically the element that you're looking at in that case. So let's try to make this a bit explicit for K2 of Q, for the simplest field. So K2 of a finite field turns out to be trivial always. So let's look at K2 of Q. Well, you can actually compute this. So you can take a direct sum of all the prime numbers of Fp star. And then, well, of course for 2, F2 star is only one element. And sort of for compensation, you sort of seem to have two more two-torsion special in there. And you're going to do this as follows. So if you take a... Okay, let's start with this one. So one of them, you look at the signs. If you look at a generator A, B in K2, then you map this to -1 if A and B are both negative, and you map it to 1 otherwise, and you may check that it satisfies the... this is the wrong way around. That it will respect those relations. Okay, so for example, this one was very clear because you cannot have both A and 1 minus A to be negative at the same time, so this will certainly be killed by this T infinity. And then for the prime numbers, you need something else. So you're going to count the number of vectors P, prime number P in a rational number. You call this well, the valuation, and you compute A to the number of vectors P and B. And here you reverse this. So if you now check, there is no vector P in this quotient at all. So you can reduce it modulo P and end up in Fp star. So this would satisfy the first two relations, but not the third. And it actually turns out you need a sign in order to fix that. Okay, so this is called a tame symbol at P for Q in this case. And then to actually compute this, it turns out to be very simple once you get your head around to it, because the only thing you need is division with remainder in the integers. Because, well, that will basically give you something like this. And if I now bring QB to the other side and divide by R, I get this one and they end up to 1. So this is a Steinberg relation. So by doing this in a moderately clever way, you can actually really check that this is K2 of Q. And well, even here there is a link with arithmetic, because there's a link with quadratic reciprocity. So quadratic reciprocity is about the question if P, prime number P, is a square modulo Q, is Q then also a square modulo P? And Gauss set this up and found an answer. That is a reciprocity law. And you can, well, if I take my tame symbol at a prime P, this is an Fp star. If I raise it to the power P minus 1 over 2, I get plus or minus 1, ignoring P equals 2. And you can, well, there's also some kind of Another map you can get from K2 of Q to plus or minus 1 by looking at what happens for 2. So you first take out of a number all the powers of 2. Then you consider it modulo 8 basically, and then you need, there's a plus or minus 1 times 1 or 5. And you take out at most 1 factor minus 1 and at most 1 factor 5. And then what you have left over can be written as a quotient of numbers congruent 1 modulo 8. So you do the same thing with a B. You get things with capital I, J, and K, and then you write down this funny sign here, and it actually turns out this respects those relations in K2. So this will give you a map from K2 of Q to plus or minus 1. And then the theorem is, you can prove at least that, well, I have now this mapping to plus or minus 1 in infinity, this one would be mapping there, and I have another one, and there's this relation. Okay, in order to prove this, you actually put in quadratic reciprocity. But you can also get it back out of this. Okay, so quadratic reciprocity is saying, okay, you have the symbol P over Q, which is equal to 1 if P is a square modulo Q, or minus 1 if it is not. And you can just check this by computing P to the power Q minus 1 over 2. Take P and Q to be odd, say. And that's exactly what you get if you compute your tame symbol at Q of PQ to the power Q minus 1 over 2. Okay, so if you now take the relation that I wrote before, and I take, say, odd primeness P and Q, well, this was based on the sign, so this is going to be 1. For this, you're going to get this whole mess made explicit, and this is going to be, well, you also compute this. Okay, so this is the one on the left-hand side. Those are the only 3 terms that you have to compute on the right-hand side, and if you just go through what comes out, this will be exactly this one. And this is, well, the symbol as explained here. Okay, so the beauty, or at least the usefulness, I think, of formulating it in K2 of Q is that if you normally do quadratic reciprocity, you have to worry about, say, if you have A divided by B or A over B, which you can try to make sense out of by the Jacobi symbol, you have to worry that they're relatively prime. Okay, you have to worry about signs and all kinds of things, and this K2 doesn't care, it always holds. So it's sort of at least a cleaner way of writing the stuff you know about quadratic reciprocity. Anyway, so this is some links between K2, K1 and K0 with number theory. And then, as I say, Quillen in the 70s defined K-groups for rings and, say, varieties. And then they were wondering, given all this background information, if there was maybe more of a link between the K-groups that has just been defined and maybe the, say, the Zeta function at some other integers than 1. And it turned out to be the case. So Quillen, so let's recall actually K0 of the ring of integers of a number field, I already stated was Z plus a copy of the class group. The K1 was the units. And, well, before you go anymore, you have to know that those mysterious K-groups are finely generated. And, yeah, it's actually a strange topic to talk about K-theory in a colloquium talk, because it's essentially impossible to give a definition and explain it. But there's a nice story about this that maybe you recognize. But, so when I was a graduate student at the University of Chicago a long time ago, Spencer Block was so our joint supervisor, was teaching a course in Algebraic K-theory. And then after 2 or 3 weeks, he realized he'd completely forgotten to give an introduction what the course was going to be about. That's what we normally do. So he stopped, and he paused, and he thought a bit, and then he said, Algebraic K-theory is a functor that takes your favorite exact category, you don't need to know what it is, and associates to it abelian groups Kn and at least equal to 0, about which you know nothing, and proceeded teaching the course. And that is actually a very workable definition, because even if you read all the stuff by Quillen, etc., you get properties, etc., but it's very difficult to compute those groups. Okay, you get nice properties and some notation, but what on earth is going on is almost impossible to tell. Anyway, so Borel managed to go beyond that stage, at least for number fields or rings of integers. So let me just say what he found out. Your K2n, so the even K groups, except for K0, because it contained a copy of Z, is going to be finite for rings of integers. If you go to the odd ones, then it depends whether you write as K2n minus 1, it depends on whether n is odd or even. So n equals 1 was going to be K1, and I've already stated what that one is. Okay, by the way, notice the minus 1 here, it's going to be important, because Yeah, okay. So if you take k to n minus 1 and n is going to be odd, then the rank should be, it should be a finely generated abelian group. The rank should be R1 plus R2. So if I here take n equals 1, which is forbidden at the moment, then I will get R1 plus R2 minus 1. Okay, it's almost the same, but as a correction term, corresponding to the fact that the zeta function has a pole at s equals 1 and nowhere else. There's only one times that the correction occurs. If you take n even, you get R2, the number of complex embeddings. And moreover, you can take this abelian group and modulo torsion, you can stick it as a lattice, so something of maximal rank inside the corresponding R vector space. And the volume, or of a fundamental domain, let's call this Vn, is related to the zeta function of the number field at n, up to, say, a non-zero rational number, some power of pi, and again the square root of the discriminant, the absolute value of the square root of the discriminant that we saw before. Okay, so main topic here is the relation between the zeta function of k at n and something, the regulator coming from k to n minus 1. So let's see what it says if you take simplest number fields, q with ring of integers z, then, well, the zeta function is just the Riemann zeta function. The even k groups, well, the even k groups are going to be finite in this case, but ignore that here. If I take k to n minus 1 with n even at least equal to 2, then this will be finite. And if I take n at least equal to 2 and odd, then this k group has rank 1. And then the relation with this regulator, this volume, is going to be some non-zero rational number times the zeta value at n. So if you make a little table, you see that we go back to the first slide essentially. Here I have the rank of the k group of k to n minus 1 as n is 2, 3, etc. And that is related to the zeta function at n, which I wrote down here, what we know about it. And I think it should be clear from this picture is that the reason that they know nothing about zeta 3, zeta 5, etc. is that they're somehow staring at the regulator of this k group. And that sort of explains why this the zeta values at the odd positive integers are really different from the even ones. Okay, so there's this k group hidden there that makes it very difficult to analyze. Okay, let's see, because people then started to think, well, you know, there is some other arithmetic one can do. For example, if I have a curve over, say, q, then I can also write down something like a zeta function. Is there maybe a relation between the k group of the curve, which has just been defined, and this L function, as it's called, which was probably at least, well, something between half a century and a century old. Okay, so let's actually say that we take something in projective space, but if you don't like this, just put capital Z equal to 1, in which case I get an equation in x and y, I get something in the plane. It's called an elliptic curve. And there is a little bit of a condition that you avoid singularity, so let's do that. And if I take integer coefficients here, I can reduce by coefficients modulo the prime p and also work there, and I get something similar. So what you can do, you can look, if you reduce your curve modulo p, you can look at the number of solutions you're going to get there in fp. And that is basically almost the same as 1 plus p. In fact, this error term lies between minus 2 squared root of p and 2 squared root of p. Okay, so this is essentially 1 plus p. And then classically they had given the following sort of local factor for, well, the zeta function, for the L function, 1 over 1 minus ap p to the power minus s plus p to the power 1 minus 2s. Okay, there are reasons for doing that, but that's what they had found classically. And, well, in case you work modulo p and there is not a nice curve there, there's also some other definition, which is, what comes out is simpler, but the definition is more complicated. And then, just like for the Riemann zeta function, you take the product of all those factors of all the prime numbers. Okay, and it will converge slightly worse. You have to take the real part of s bigger than 3 over 2 in this case. Okay, so this is the analog of the Riemann zeta function, or the zeta function of a number field. And so then Spencer-Bloch thought there may be a relation with k2 of a curve. And how are you going to compute that? Well, because of his attitude or equivalence definitions, you're not going to do that unless you trick yourself around it. So the way to do it is, if you sort of remove points from your curve, you sort of end up only with, well, the functions on the curve, in some sense, in this algebraic sense. And you can, well, this is one of the properties that Quillen proved, that you can sort of take the K2 of the curve, you can then remove more and more from the curve and take only the function field. And then there is a boundary map, which is essentially given by the same symbol. So I take a point in the curve, and then, well, before for Q, I counted prime factors in symbols in A and B, if A and B was a symbol. And here, counting prime factors would be replaced with looking at the order or vanishing of a function. So it could be a pole or a zero. And then if you take functions f and g, and you map a symbol f comma g to this thing, again, if you compute here, this has neither a zero nor a pole at your point x, and you can restrict it to x. Okay, so this is going to be, again, something that that gives a map from K2 of the function field of curve on functions on the curve to this here, and the kernel will be coming exactly from K2 of the curve itself. So the idea, Spencer, was that if you cannot compute this thing here, at least hopefully you can compute something in this kernel here, and that comes from there, the best approximation. Okay, then we need something like, well, like the log of the absolute value, for which is the case for units in the ring of integers of a number field. It's going to be slightly more complicated in this case because you have two functions. So let's take functions f and g, and I can take the log of the absolute value of f. That's a nice function. And well, I could take the argument of g, but it is not such a nice function because it's multivalued, because it's valued by multiples of 2 pi. But if I differentiate, compute the one form, the d, then I get rid of this local constant and I get a nice global one form. So because of the properties for f and g, it's essentially alternating. You take the log of the absolute value of f, the argument g, and minus, and then you swap the f and the g. And if you go back to K2 of a field, there were three relations. Well, the first one had to do with multiplication versus addition, and the log and the argument will be exactly right to do that. But the third one was something of the form sort of f comma 1 minus f to be trivial. So if we work on the affine line with coordinate z, then it would have to show that this one becomes trivial. But you can just sit down and integrate. It turns out to be a closed one form, and the residues are 0, so you can just integrate to a function which is called P2, Bloch-Wigner dilogarithm. And then you can map, therefore, your K2 of f2. Well, it becomes slightly messy here, but you're going to take this form, and it actually turns out to be closed. If you differentiate it, it's going to be 0. But then modulo the d of functions, modulo what are called exact forms, this will make sense. Okay, and there is a further issue that, of course, if I have random f and g, I don't have a clue where the zeros and poles are, so I have to be rather flexible about allowing larger and larger sets of zeros and poles. It gives the following picture. Let me start here. So in algebraic topology, you could look at h1 of an elliptic curve. This is just a torus, so it's h1 because it has two loops and two directions. And you can then sort of remove a few points, because I have to allow zeros and poles. And then there is a boundary map, a residue map basically, that computes locally the residue of a one form. Okay, so again, this is what is called exact. The kernel here is exactly this one here, and this one injects. And then you can build a picture as follows. So this is the map that I had on the previous slide. You take a symbol f comma g, you map it to log absolute value of f d argument g, etc. Here was the same symbol, and here you just take the log of the absolute value, and then you can check that this thing commutes. So just formally, then you get a map from K2 of EC to this one, to the global one forms. Okay, and then if I started over Q, I first extend the coefficients to C, and then I get this map. Okay, so you trick yourself around it. And then Spencer proved that there indeed is a relation with the L function. So you take a holomorphic one form. So if you see your elliptic curve as C modulo, say, some letters in the plane, so you get the torus. You have dz on there, and you have to scale it a little bit maybe to get this omega, basically. But then you take your element in K2, that Spencer wrote down quite explicitly, you compute your regulator, you pair it with this omega, you get a 2 form, which you can integrate over your torus. And then again, it is related to, well, not the L function at 2, so in this case the L function at 0, but that is 0, but you can do it to the derivative, which is non-zero. And again, there is a rational number there. I should say this is done for a special type of elliptic curve, because normally if you have this torus, you can only multiply by an integer. But for example, if you take something like C modulo z plus zi, then you can also multiply by I. You have more than just multiplication by integers. It's called CM, complex multiplication. Okay, and then there is actually a known relation in that case between what happens around 0 and what happens around 2, and you can also rewrite the relation like this. Okay, so it's the same idea. You get the regulator of the K group and you relate it to an L function up to a non-zero rational number. Okay, so Beinussen then came along and he looked at this, the results of Borel and what Bloch had proven, and he made a very general conjecture about relations between K groups of varieties over number fields and L functions. Very complicated to state and essentially impossible to prove. But the principle is the same if you are going to look at this a little bit. So the simplest case I'll be looking at is K2 of a curve. So it will no longer be elliptic, it may be more complicated. But you have the same principle that you're going to remove points from the curve and you then look at K2 of the number field. You have a tame symbol again, which is defined as for elliptic curves by looking at orders of vanishing at a point. And then here I've described the incoming stuff that describes the kernel here. K2 of, well, the field of the definition of a point P. Which may be larger than Q. But we're going to ignore that because we've seen what this is for Q. It is an infinite torsion group, and in general it will be an infinite torsion group for a number field. And this stuff is so difficult, you just ignore torsion anyway, so just ignore that. In that case I can sort of say that this one is the kernel of this map. And then they did some, well, actually Bloch and Grayson did some computer calculations checking if this kind of relation would hold more generally. And this became a big headache. Because it didn't work. They tried elements in K2 and they computed this kind and they tried to relate it to that and it simply didn't work. And then it turned out, well, two things happened simultaneously. Then Grayson, I don't know if you know him, but he's also one of the authors of the Mathematica package. He wrote routines for just computing with higher and higher precision, because they simply said, oh, this rational number must be very complicated. It's a big denominator. We need, we need hundreds of decimals and then we can recognize what it is. And Spencer Bloch had a sleepless night, in which he realized that if you look at what they started from originally, if you look at the residue at s equals 1 of the zeta function of a number field, you don't look at the k1 of the number field, you look at k1 of the ring of integers. Because the k1 of the number field, be all the units in the number field, is very big, and you need something much smaller. So they then decided, or Spencer Bloch decided, that they should not be looking at K2 of the curve of a Q. They somehow should look at what happens modulo all the primes as well. So this happened at the same time. And so when they got together, they A, imposed another condition, and B, they computed with hundreds of decimals of precision. And this is the right thing. So once they then calculated the numbers in here, I think the worst denominator they ever found was 7. So they would find 1/7, but then up to 300 decimals of precision. So, by the way, this is interesting in the sense that the routines that Dan Grayson wrote ended up in Mathematica. So the reason that you can calculate up to arbitrarily large precision in Mathematica is because there was a wrong conjecture in K-theory for curves. It's a kind of bizarre way of how things go in practice. Anyway, so let me say that you can compute K2 of C, or you can pretend to compute it like the kernel of this same symbol, and then actually need a condition in there. So you ignore the torsion all the time, but this is too big. You therefore describe some precise subgroup in there by considering what happens modulo all primes. And then Beinussen had the following idea. Well, so you believe that this thing is a free Euclidean group of rank G. Well, sort of he tensors it with Q. It should be a Q vector space of that rank. The genus. Okay, so for a torus, the genus is 1. In general, it will be the number of holes in a Riemann surface. And you can look on this Riemann surface. Well, there's a complex conjugation because the thing was defined over Q originally. And the H1, the loops, there will be 2 times the genus, but sort of half of them are anti-invariant for complex conjugation, and half of them are invariant. So if you take the anti-invariants, you can get G of them, and you compare those with hopefully the G elements that are independent here. In the following sense, you write down the regulator, and you integrate over a loop, and you normalize a bit. Okay, so hopefully you get a square matrix, and then if you take the determinant of this pairing, you take the absolute value, then that should be related to the L function at 2, given some up to some junk factors there. Okay, so this is essentially impossible because you can compute your homology, but you cannot compute the K group. So what you do in practice is you find G elements in K2 or the subgroup defined by Beinussen, and then you just use this in 3, and then you see if the relation with the L function holds, either numerically or theoretically. Okay, so here you have a simple way of finding elements in the kernel of the same symbol due to Bloch. And suppose I have only 3 points that I want to use in the curve with rational coefficients. And now suppose I have a function, say f, which has 0 at p, pole at O, and no other zeros or poles. And you assume you have the same thing for q with the function, okay, fq here is called 0 at q, pole at O, and nothing else. And if you then normalize them, because I can fp, I can scale to 1 at q, and conversely, and then you can check that this symbol is actually in the kernel of the same symbol. Okay, so there's a very clean way of getting that if you can find such points. So here's an example that I did about 10 years ago with Tim Doxers and Don Zergay. I wrote a paper where we do this for hyperelliptic curves that map P2 to a P1. And you take very special ones. So this is the kind of equation that we want. So what I would like here, if I want to have genus 2, would be a polynomial would be 5 in x. And no double roots, some simple conditions. But in order to get the p and the q that I want, because the point O will be lying at infinity, that you get, you take some really special ones. I take something to the form a squared minus b squared. And of course I can factorize this as a plus b times a minus b. So, well, that you do. So here is my polynomial p, and then if I do this, I get p minus 2x cubed and p plus 2x cubed as the factors. And then you can write down the functions that you want, because if I take y minus px, meaning I plug in y equals p, this will cancel, and therefore I get x equals 0 6 times. So that will give me actually 6 times this point, and the pole will be at infinity. Well, you can do the same thing, but then using the other shape here. If I put in x plus 1 equals 0, this becomes 0, and therefore y is 0 with multiplicity 2. Okay, so by taking the right shape, you can trick your way around this, and you can get some elements. In this case I need 2, because the genus is 2, and you can write down what this construction of Bloch gives, and you can rewrite a little bit, and you get 2 elements. And you stick this into the computer, and then you find that indeed the regulator that comes out is related to the L function with normalization by some rational number. Okay, so very simple factors. The only point is in the functional equation, so there should be some relation between what happens between 0 and 2. This is what is called a conductor, and that shows up all the time, so it's been written separately, and that is actually contains at least prime number 59. Okay, so then more recently I had a visiting PhD student from China, Hang Liu, and he was very interested in K2, and we cooked up some new constructions because the previous one said is hyperelliptic. And well, in some way those curves are quite special. You would like to have more general curves, and here are some more general ones. So what we do is we take, in this case, 3 lines. So I take some vertical lines, and you take some horizontal lines. And if you feel like it, because this n3 may be 0, so this vector may not be there, but if you feel like it, you may also take, say, some diagonal lines like this. Oh, sorry, actually the diagonal is the other way around, I think, in this case. And then you basically deform this a little bit. So this would happen if I take this product equal to 0, but that is basically what happens if I take this on very large. Okay, so the curve that you define by putting this equal to 0, trying to approximate this picture here if I take my lambda to be quite large. And you can also, because of the special shape of the equations, you can write down some elements. So, for example, if I take this thing here, I take the coefficient of 2 vertical lines and here 2 horizontal lines. And if I were to, for example, go very high up, I let my y get very big, then I will be approximating the points where there's a 0, but y is going to be very big, so this is going to be 1. Okay, so you just check that indeed the same symbol is going to be trivial all the time. And well, we cooked it up in such a way that also this special condition of the subgroup of Beinersen is also going to be satisfied. So this is what you can do if you have only horizontal and vertical ones. And if you also have the diagonal ones, then you can have a small variation. You can throw them in like this. So this one really corresponds to sort of basically what you can do with a rectangle, and this corresponds with a triangle. And there are lots of relations among those elements, because, for example, if you were to write down this rectangle and I split it into 2, then sort of according to your feeling, this one and this one should end up to the big rectangle. And there actually is a relation among those elements that matches exactly that. And similarly, you can have you can split your triangles in a formal way, and it's for some bizarre reason you can actually prove that those elements satisfy the same relations. Okay, so in practice there are not as many elements as you would hope. Well, there are, but they're not independent. But you can write down some relation. It turns out that the number of okay, I wrote down the genus. So this thing looks like a Riemann surface over the complex numbers with a number of holes called a genus, and the formula for the genus turns out to be this one for almost all lambda. Could be a few exceptions. And it turns out that if you actually compute with all the relations you can find, then the number of independent elements you can get is at most this genus. Okay, so that is exactly what Beinersen would like to have, but then you have to prove that they're independent. And of course you cannot do this in general because after all this is K-theory and you know nothing about what you're doing. But you can actually take a limit in this case. So as I already said, if I now fix my alphas and my betas and my gammas and I let my lambda run, it had to be an integer, I can make it arbitrarily big or arbitrarily negative. So the curve is genus G in general. And in that case actually the elements that you get, the remaining elements, are really independent. And they're in this special subgroup, and you know they're independent because you compute the limit of the regulator. Right? The regulator in this case becomes basically a function on the lambda, and then it behaves essentially like the log of the absolute of lambda to the power g. And of course, if it gets close enough to be non-zero, then I know that the elements must be non-zero because must be linearly independent because well, this regulator came from a determinant in the end. Okay, so that means that in practice you have at least the right number of elements as conjectured by Beinersen. Of course, what you do not know at all is that they would sort of span the subgroup generated, the subgroup that Beinersen would like them to span, or maybe be a finite index in there. And also the one thing that we didn't do is we did not try to relate this to the special value of the L function. Numerically, one could simply try and do that, but it's going to be a bit of work and we didn't do that yet. Okay, that's what I would like to say. Thank you very much for your attention.